Okay, today we're going to learn about Anova, the analysis of variance. And despite its name, it is a way to compare means among two or more groups. Now, we're going to stick with three or more groups because we'll use the two-sample t-test for two groups. And actually, the Anova in a two-sample t-test for two groups will give you the same information. So what do we do when we have three or more groups? Well, we can't do a bunch of multiple t-testing. The problem with doing a multiple t-testing, say like I want to compare the effects of aspirin, ibuprofen, and control. I can't do t-test aspirin versus ibuprofen, aspirin versus control, ibuprofen versus control. The problem with that is that we start inflating our error. Okay, what do I mean by this? In your book, there's a joke study on the butterfly effect where butterflies were measured for their flapping rate in the United States and when it would rain in Paris, and then they found one butterfly that they said was statistically significant, the one who was responsible for rain in Paris. It was called data dredging. And they conducted a bunch of different tests until they found one that gave them a p-value below the alpha of 0.05. So the problem with that is that when you do a bunch of multiple tests, you're inflating your type 1 error for the data. And this is especially why we don't do multiple t-tests to tell the difference between three or more groups, because we will be inflating our type 1 error above 0.05, and that's why we don't do it. Methodology. So the Anova. So it is done in two stages, and there's an omnibus test for differences among the means. And it generates an F statistic and its p-value. Now, we've seen that F statistic before. If you recall, Levine's and the test for equal variances used an F statistic. And we're using the same F distribution here. The F statistic is calculated a little bit different because here in the Anova we're looking at whether variance between samples or between the groups is equal to variance within samples. And of course, if it's equal in a ratio, they're going to equal 1. So we're going to keep our alpha at the same, and this omnibus test, while it tests for more than two groups, does not inflate the type 1 error. The omnibus test will only tell us that there's a difference somewhere. It doesn't tell us where. So if we get a significant F test, high F statistic, low p-value, we'll follow it up with a post hoc procedure, which also does a bunch of multiple group comparison, but does not inflate the type 1 error. So how do you compare means when you're talking about variance? Well, here's what we're going to do. We're going to look about variance in groups. So we have variability of group means around an overall grand mean. I like to call it le grand mean. What's a grand mean? That's taking all the data, no matter what group, and putting it all together and creating a mean, calculating an arithmetic mean. So we want to look at variability of group means to that grand mean, the grand mean, and we also want to look at variability of all the data points around that. Then we also want to look at variability within the groups, and that's data points around their own group mean. Okay, so we're looking to see if means are really different from each other. There's going to be a lot of variability of the means compared to the grand mean, versus a lot of variability within the groups. All right, let's keep looking. Here are our sources of variation. We have total variation. That's the data points, all the data points to the grand mean. That's the black horizontal line. So le grand mean, how far are all these data points from each one? Then in the second one, the group's variation, and this can also be called treatment variation. We'll see how far the means are of each group to that grand mean, how far away they are. And in the final error or variation, which we call error, that's each individual data point within the group and how far it is away from its own mean. That's the unexplained random individual variation, stuff we can't explain. Hopefully biological variability. All right, let's recall our definition of variance. Okay, it was the sum of every data point and how far away it is away from its own mean, squared and divided by the degrees of freedom. So that top part, SS, is the sum of squares. And we're going to be interested in the Anova to break this down into parts and use this in order to tell us where if there's a difference between means. So that partitioning, that breaking down, we have three sources of variation. Sum of squares total, data points around the grand mean, sum of square groups, group mean to the grand mean, and sum of square errors, variability of data points around its own mean. Slide again, you can see this is the partition. So this is you saw the slide before, now we're looking at it with the calculations. And the fact that sum of squares total is additive. So sum of squares totals equals sum of squares groups plus sum of squares error. Okay, so it's additive. So we can see in the first part we're looking at every data point and its difference from the grand mean. Notice that Y in that sum of squares total calculation. Double bar. Double bar is the grand mean. Okay, second sum of squares, each group's mean to the grand mean, and notice we use the group size in that calculation there. It sort of weights that for every sample size for the group. And then sum of square errors, which is what we're sort of used to. Every data point in its group and its difference to its own mean. All right, degrees of freedom can be partitioned just like sum of squares can, and it is additive. So we have a couple new letters to denote certain things. Capital N here is the sample size for all the groups. So adding up all the data points in all the groups, that's the sample size. K here is the number of groups. We'll use lowercase n to denote a single sample size for a single group. Uppercase N, sample size for all the group. Okay, and so degrees of freedom total, capital N minus 1, degrees of freedom groups, excuse me, K minus 1, degrees of freedom error equals N minus capital N minus K, and again, additive. So now we can start calculating the variances. All these variances, the mean squares. Okay, so mean squared is the sum of squares divided by its corresponding degrees of freedom. So mean square total is sum of squares total divided by degrees of freedom total, and so on down the line. The thing to remember here is that the mean squares are not additive. We do not have that relationship anymore because as we've divided by its each of its degrees of freedom appropriate to the total, the groups, or the error, that changes that relationship. So it's not additive anymore. All right, so what are we really asking as the null hypothesis in Anova? The null hypothesis is similar to what we've seen before on the first hand, except we only had two groups, right? The mean of group 1 equaled the mean of group 2. That's what we did for t-testing. So we're just adding more groups here. Okay, and here we have a 3-group comparison. The other thing to really think about, and this is important in terms of our F statistic, is that the null really is that the mean square of groups is equal to the mean square of error. Okay, and I'm going to be calling this noise and signal to noise. But let's keep going. So what we're saying is under the null, any differences among the means from that grand mean is due to random sampling, right? It's random error. There's no treatment effect there. That's what we're saying under the null. So if it's true, that mean square error of groups is going to be the same as the mean square error, right? And that mean square error is that random error that we see within a group. Okay. So let's unpack this a little bit more. So what we're going to see is a higher sum of squares group, okay, and then a higher ratio of mean square groups to mean square error when the difference between those means is larger. Okay, so in this first example, group 3 is really the odd man out there. That's a big difference between the groups, particularly for group 3. And so that's going to drive this to be larger. And it's going to mean that mean square groups is going to be larger than mean square error. Okay, they're not going to be the same. Now we're going to get lower sum of square groups and a smaller ratio of mean square groups to mean square error, or the fact that they're more equal when there's not a lot of difference between those groups. So you can see those means aren't very different from each other. So what's going to drive that is the denominator, right? That random variation from each group to its own mean. So it's going to make that smaller. So when we're testing for differences among means, what we're going to do is we're going to create an F statistic. Okay, so under the null, like we said, the mean square groups equals the mean square error. And so we know that the F statistic is a ratio, so we're going to take that idea under the null, and if we put them on top of each other in a ratio, that's going to equal 1. Okay, so under the null, the F statistic is the mean square of groups over the mean square of error, and it should equal 1 under the null. And then we're testing, well, how far away is our F statistic from 1? Because we're going to get a probability associated of how far that F statistic is from 1 under the null. And again, I'm calling that the signal to noise ratio. So if mean square error of groups is big, a lot of difference between means to the grand mean, that's going to make our F statistic larger versus the noise in the denominator, which is the individual variation within the groups. Okay, so what you get in Anova is an Anova table. And so it's built on these variance calculations that we've been talking about. So let's see how we build it. So we have sum of squares, we have total, arrow pointing to where that is in the table, sum of squares between groups, oftentimes called sum of squares for treatment, because we're saying that the difference between there is driven by whatever treatment you used, a control and two groups that varied in the treatment levels, something like that. And then we have the sum of squares error, right? The individual variation to its own mean. How do we do this? All right, so here's some sample data, and we'll play with this more in class. In group 1, we have, we create a grand mean. You can see that in the third column there, the grand mean. And we take every data point in every group, and we subtract that to the grand mean. And then we square it. Then we add it all up, and that becomes sum of squares total. Okay, for the error sum of squares now, we're taking each group's data point minusing its own mean. So see that every group has its own mean that we're subtracting its own data point from. Okay, and then we square those, we add those up, that's sum of square error. Now because they're additive, we could figure out the sum of squares group by taking the total minus the error. Or we can use the formula, and here you can see the formula. Sum of squares groups is the sum of the sample size of the group's mean minus the grand mean squared plus the next group plus the next group. We add them all up, and that's sum of squares group. Now we'll put in our degrees of freedom for each partitioned variance. So degrees of freedom for groups is k minus 1. There's 3 groups, so that's 2. Sum of squares, degrees of freedom for sum of squares error is all the data points, 22 data points, minus k, so capital N minus k, and that's 19. And finally, for sum of squares total, the degrees of freedom is capital N minus 1. Now we can calculate the mean squares and the F ratio. So we divide the sum of squares for groups or treatment divided by its degrees of freedom. There's the mean square. We divide the sum of squares for error by its degrees of freedom. We get the mean square error. We actually don't need the mean square for the total, so it's not used in the calculation of the F statistic. So we just need those two. So generally those are the only two mean square values you're going to see. The F ratio then is, and this is our F statistic, mean square error groups over mean square error, and it's 7.29. Now we want to know, is that rare? Does that result in a low p-value? Okay, in Minitab, this Anova table is going to generate automatically. If we're doing it by hand in Excel and we've gotten all these sum of squares, degrees of freedom, and mean squares, which if we have time we're going to do, then in Excel we can get the p-value for that F statistic using the FDIST formula, where we have the F value we got, the F statistic, the numerator degrees of freedom, denominator degrees of freedom. Why does that matter? Because the we are basing this on the shape of that distribution is dependent on the numerator degrees of freedom and the denominator degrees of freedom. So just like T, there's a bunch of T distributions, there's a bunch of F distributions based on those degrees of freedom. And just like we saw in the t-test, we can get a critical value that we know our F statistic has to exceed in order to have a p-value below 0.05. In this example, we had 2 degrees of freedom in the numerator, 19 degrees of freedom in the denominator, so F critical is 3.52. And we saw that our F was indeed above that, which resulted in a p-value below 0.05, and we got the exact p-value of 0.004. So what did we conclude? Well, we're certainly off this omnibus test. So that's what we've seen before. The Anova F statistic generation and its associated p-value is our omnibus test. And we're going to reject the null here. Now we're going to see it's about light, but we'll go over that in class. The problem is we just know from the omnibus test that there's a difference somewhere in these groups. It doesn't tell us exactly where. So if we get a significant high F, low P, and we're going to reject the null, we need our post hoc. So we use the Tukey-Kramer method. And again, we only use it when we have a high F, low P. And because that's where we want to say, hey, where does this difference in means lie? Who's different from who? So again, we only use it when we have a significant omnibus test, the F test, the Anova table, showing a high F, low P. Because if we don't have that, we're saying all the means are the same, so we don't need a post hoc. So here's Tukey-Kramer. Okay, I'm going to show you what it's doing, but we're never going to do this. We're just going to look at the results of those from Minitab. But basically, they order the means, and they do a bunch of pairwise comparisons, and then they like to see who's different from who. Here's the idea, comparing first group to second group, group 1 to group 2. And it gets a new test statistic. It has a critical value. And you can see here that based on this Tukey-Kramer, group 1 and group 2 are not different. We retain the null. Those two aren't different from each other. However, it's group 3 who's different from everybody. It's group 3 who's different from group 1 and group 3 who's different from group 2. And what you get from Tukey-Kramer is actually not that table I just showed you, but you get an output showing letters for each group. And so in this case, we've rejected the null because of our omnibus Anova table and our F statistic with a low p-value. And now we see these letter designations, and indeed, it is group 3 who is different from group 1 and group 2. The last thing that we can get from Anova is, okay, it's statistically significant. We know who's different from who, but what we want is some idea of an effect size. How big is this difference being driven by the treatment that we used? That's basically what we're asking. So we get an R squared value, And that's where we use total sum of squares, because it's group sum of squares over total sum of squares. So it's the proportion of variation in the response, our outcome variable, that is due to the predictor or explained by the predictor. What's the predictor? It's our treatment. Whatever we did, that is the difference between our two groups, the thing we tweaked. Okay? The higher it gets to 1, the more variation is explained by what we did in our treatment. This example we've been running through with this data, the R squared is 0.445, so that's 44.5% of the variation between groups is due to the treatment. Whatever I tweaked, the difference between these 3 groups. Okay, so it's a much better measure of effect size than p-value. And so when we see an R squared of this magnitude, that's right about right in the middle. So there's a lot of gray here. So 0.5 and above, 0.5 would be moderate. And as we get higher towards 1, it gets greater. And of course, as we get lower than 0.05, we get small effect sizes. Of course, there's assumptions of Anova, of course. And we have independence of observation, random sampling. That's not going away. We want normal distributions again, and we want equal variances. Now we don't call it homogeneity of variances, we call it homodiscacity. And we can use the Levene's again here, although it's found in a different spot. I'll show you in Minitab. Of course, Anova, just like the t-test, is robust to deviations from meeting these assumptions when we have large sample sizes. So we can use our Levene's test and our AD plots to check for normality and equal variances, and I'm going to show you that in class. But we have an additional piece of information that is actually probably maybe even a little bit better, which are called residual plots that we get from Anova. And these residual plots tell us about our assumption. So here's what we get, this 4-in-1 plot. So in the upper left corner, normal probability plot of the residuals. Okay, you're saying residuals. What are residuals? Residuals are the data point and its difference to, difference, I guess I'll say, or distance to the mean. Okay, so whatever residual we're saying, difference to the grand mean. So however far away it is in the units we measured. So in the first plot, the normal probability plot of the residuals, all those residuals should fall along the line, and that means overall we've got good normality. In the residuals versus the fitted values, we should see all those residuals equally on both sides of 0. That means equal variances. For our histogram of the residuals, we should see basically a bell-shaped. Okay, and this is a new one, and this actually is our first ability to have a quantitative way to look at whether or not we have independence of observations. So we've never had this before. And what we should see is these points should kind of go up and down along the line randomly. We shouldn't see any pattern, like big up and down at the beginning and very little up and down as we go along in the order that we measured our observations. So they should just go up and down randomly, no pattern. That's what we're looking for there. So finally, transformations are appropriate for Anova. We could do log transformation if we didn't have the large sample sizes, and we couldn't ignore the assumptions, so we could do a log transformation here. We also have a non-parametric alternative. It's similar to the Mann-Whitney. It does ranking, and it's called the Kruskal-Wallis. So you'll see that under Minitab under the non-parametric tests as well. And we probably won't go over that in class because I really want you to just know how to run an Anova in general first. Okay, and that's it.